Good day, this is Dr. Wortel with a revision lecture on how to prove limits. Okay, so what is the setup? So we have some function from R2 to R, and what we want to do is we want to prove that the limit for the vector for xy going to the fixed vector AB of fxy is equal to some fixed value L. Okay, so let's first look at the definition of this limit. So this means that for all epsilon positive, we need to find the positive delta with the following property. That if our point xy is close to the vector AB, in the sense that their distance is strictly bigger than 0 but less than delta, then the distance between fxy and L has to be less than epsilon. So in other words, given an epsilon, we need to find the delta in such a way that if the distance between xy and AB is less than delta, then we are able to ensure that the distance between fxy and the number L is less than epsilon. So the proof technique that we're going to use is the following. We're going to start with the thing that we want to estimate, so the absolute value of fxy minus L. And we're going to estimate it by something in terms of this quantity, the square root of x minus a squared plus y minus b squared. Why do we want to do that? Well, this is precisely the distance between the vector xy and the vector AB. And because we can pick our delta, we can basically get this as small as we want. So if we can estimate this by something that we can get as small as we want, we are also able to get the absolute value of fxy minus L to be as small as we want. One quick remark before I go on with the example, that if the point AB or the vector AB is the origin, then this expression here, the square root of x minus a squared plus y minus b squared, is just equal to the square root of x squared plus y squared. So it's a little bit easier in this case. Okay, so to explain what kind of techniques we're going to use, I will do everything with an example. So the example that we're going to discuss is to prove that the limit for xy going to the origin of sine y x squared plus 4y to the third equals 0. So let me go to the next page. So as I said before, this is what we're going to prove. We're going to prove that the limit for xy to the origin of the quantity sine y x squared plus 4y to the third equals 0. And then from the previous slide, we saw that the proof technique was going to be that we start by estimating the fxy minus L, and we want to estimate it by something like the square root of x squared plus y squared. So that's going to be the goal. Okay, so let's start by the absolute value of fxy minus L. What is this in our case? So our fxy, that is this quantity over here, and our L is 0, right? So what we get is the absolute value of sine y x squared plus 4y to the third minus 0. Okay, well, obviously the minus 0 can just be cancelled, so we can ignore this. Okay, so a very important first technique is the triangle inequality, because we want to split up such a quantity into smaller parts so that we can deal with them separately. So first, by the triangle inequality, we can split this up as the absolute value of sine y x squared plus the absolute value for y to the third. Okay. So now we've got two terms, and again we want to somehow deal separately with the sine of y and also deal separately with the x squared. So the next thing we're going to use, let's do it over here, is we have the absolute value of a product, and it's known that the absolute value of a product is equal to the product of the absolute values. So we can write this as the product of the absolute value of sine y times the absolute value of x squared plus... Okay, now for the second term here, y to the third. Remember, our goal is to estimate it by something like this. So here we see a square root and we see x squared plus y squared. Well, here we already have an x squared, right? So ideally we want a y squared over here. But we have got y to the third, so it makes sense to say, well, let's write y to the third as y squared times y. And then we can estimate this as follows. Well, first of all, we can take the 4 out because that's a positive constant. Then we can say, let's write it as absolute value of y times the absolute value of y squared. Again, by the same rule. Okay, so now let's deal first with the absolute value of the sine. So I should probably maybe in a different color. So of course we all know that the sine of any value, theta, is between -1 and 1. So it follows that the absolute value of the sine is always less or equal to 1, no matter what the value theta is. In our case it's y. So it follows that this sine of y can be estimated by 1. Okay. So another thing that we would like to estimate is this absolute value of y. But yeah, this is not so clear. But we see here that if the absolute value of y is less or equal than 1, then we can estimate this by just 4. So for the moment, what we're going to do is say, okay, well, this is going to be less or equal. So if the absolute value of y is less or equal than 1, then we are also able to estimate this term. And later on I will explain how to work this part back into the proof. So under this condition, we can estimate all of this by so this term is the absolute value of x squared is just x squared, and then we have 4 times, and again the absolute value of y squared is just y squared, because these terms are always positive. So under this condition we have x squared plus 4y squared. Okay, now we're very close to estimating them by the square root of x squared plus y squared, but here we have an x squared and there we have a 4y squared. So what the easiest thing that we can do is say, well, since x squared is a positive number, if I multiply it by 4, it will become bigger. And that is then equal to 4 times x squared plus y squared. And now we're very close, because we need the square root of x squared plus y squared. So x squared plus y squared is, of course, the square of its square root. So this is equal to 4 times the square root of x squared plus y squared squared. Let's write it like this. Right, and this is exactly equal to 4 times this distance between the vector xy and the origin squared. Okay, now recall from the previous slide that we will get to choose our delta later, so we can make sure that this distance is less than delta. So later on we will be able to ensure that this is going to be less than 4 delta squared. However, also recall from the previous slide that what we want to prove finally is that this is going to be less than epsilon. So we want this to be less than epsilon. So I will say this is something that we want. So we don't have this yet, so let me put an error and say this is what we want. We would like that to be equal, because then if that were to be true, then this in the end would be estimated by epsilon, and that's what we want. Okay, so how can we find our delta? Well, basically what we do from here, let's continue in blue, we simply solve this equation. 4 delta squared is equal to epsilon. So it follows that delta is equal to root epsilon over 2. Right? If you solve this equation, you get delta squared is epsilon over 4, so delta is root epsilon over 2. So that would be a good delta to pick. So note that we can also pick any delta that's smaller than this, because then the same estimate is going to hold as well. Right? So we can pick this delta or a smaller delta, and then we're in business. Okay, so everything is fine now, except that there's still this problem of the fact that our entire computation is only valid if the absolute value of y is less or equal than 1. Yeah, so let's write this down. Maybe. So the entire estimates holds only if the absolute value of y is less or equal than 1. So the question is now, how can we ensure that the absolute value of y is less or equal than 1? Well, what do we have control of? We have control over the delta, and the delta tells me something about the distance between x, y, and the origin. Right? And that this was equal to the square root of x squared plus y squared. So we can control the value of the square root of x squared plus y squared. And we need to control the value of the absolute value of y. So if we can estimate the absolute value of y in terms of this term, then we're in business because we can control this. Yeah, so that's going to be the next point, is to somehow rewrite the absolute value of y, or estimate it in terms of this distance of xy in the origin, which is equal to the square root of x squared plus y squared. And how can we do this? Well, we just use we use a property that the absolute value of y is equal to the square root of y squared. And then this is very close to this distance that we're looking at. We just need an x squared. But now we can say, well, square root is monotone, so if I add something positive, and x squared is always positive, that's going to make it bigger. And that is precisely the distance between x, y, and the origin. Right? And that is something that we can control. We can make it less than delta. So now we see that if we pick delta to be less or equal than 1, then the absolute value of y is less or equal to 1, right? Because, well, if delta is less or equal than 1, let's put that in red. Then I have that the absolute value of y by this inequality is less or equal than 1. Okay, so now we have two requirements on delta. We need delta to be less or equal to 1, such that we can take this step in the computation. But also in the final step of the computation, where we get everything to be less than epsilon, we want delta to be either equal or less or equal than epsilon over 2. Yeah, so let's write this down. So we want two things. We want that delta is less or equal than root epsilon over 2. And we also, okay, let's root epsilon over 2. And we also want delta to be less or equal than 1. So now what we could do is we take the least of those, but the problem is we don't know, because the problem is epsilon is not a fixed number, right? If epsilon is 100, then 1 is the smallest of these numbers. But if epsilon is 1 over 100, then root epsilon over 2 is the smallest of these numbers. So we don't know a priori which one we should pick, but we need to ensure that both of them are true, and this is why we're just going to take the minimum, right? So we take delta to be the minimum of those two values. And the point of this is, now that we have ensured that delta is both less or equal than 1 and also less or equal than the root epsilon over 2. Because that's a property of the minimum, it's smaller than both of them. Okay, so now I will finish the proof on the next slide. So here let me just denote this whole equation by star, because that's an equation that we're going to need in the final conclusion. And we note that as long as we've ensured that delta is less or equal than 1, then the equation star is valid. Okay, let's continue with the next slide. Okay, so this is basically step 2, which is the formal proof. So we take an arbitrary epsilon and we have to find our delta. Well, we just did that, right? We just discussed, and we found that we should pick our delta to be equal to the minimum of root epsilon over 2 and 1. And the point of taking it as the minimum, as I just explained, is so that delta is less or equal than root epsilon over 2 and delta is less or equal than 1. So that's something that we can use. Okay, now if you go back to the definition on slide 1, you see that we have to prove that if the distance between x, y and the origin is less than delta, now we have to prove that the distance between fx, y and L is less than epsilon. But if this is the case, then, okay, so let's now look at the absolute value of fxy minus L. So that is, in our case, was equal to sine y x squared plus 4y to the third minus 0. Right, now we have this whole inequality star, and because our delta is less or equal than 1, maybe let's write it with red. This ensures that this inequality star was valid, because by the previous slide, then we had to have that the absolute value of y is less or equal than 1, and then our whole computation was valid. So by the previous slide, by this inequality star, we get this is less or equal than 4 times the distance between x, y, and the origin squared. Okay. Now, we're going to use the fact that delta is less or equal than that, right? So here we see that this distance is less than delta. sorry, so let's use that first. So this distance is less than delta. So 4 times the distance squared is going to be less than 4 delta squared. And now we're going to use this. Now we're going to use that delta is less or equal than root epsilon over 2. So now we have that this is less than 4 times root epsilon over 2 squared. And of course, yeah, we picked it in such a way that this is going to end up nicely. So this is 4 times epsilon over 4, which is epsilon. Okay, so let's think about what we did. We for any epsilon, we picked our delta like this, and then we proved that if the distance between x, y, and the origin is less than delta, then the distance between fx, y, and L is actually less than epsilon. And that's precisely what was needed. So now we can conclude by saying that since this holds for all epsilon, it follows that, by definition, that the limit for x, y to the origin of sine y x squared plus 4y to the third equals 0. Okay, so now here's an exercise that I want you to try. Do this yourself. So prove that the limit for x, y to the point 3 minus 4 of the quantity arctangent of the absolute value of y plus 4 to the third times x minus 3 plus y squared equals 16. So please try this exercise yourself.